Okay, so now we're moving on to section 24.3. So we can find the position and the size of the image formed by a mirror by a simple graphical method. This method consists of finding the point of intersection of a few particular rays that diverge from a point of the object, such as at point Q, and are reflected by the mirror. Then, ignoring the aberrations, all rays from this point that strike the mirror will intersect at the same point. So for this construction, we're always going to choose an object, a point that is not on the optical axis. Four rays that we can usually draw easily are going to be shown here in 2418, and these are going to be referred to as the principal rays. So number one, we've got a ray that's parallel to the axis, to the optical axis here, and goes through the focal point. Ray number two is going to be through the focal point that reflects parallel to the axis. So it comes through here, and then as it bounces back, it's parallel. We started out parallel, then goes to the focal point. This cuts through the focal point and then turns parallel. Ray three is a ray that through the center of the curvature that intersects the surface normally and then reflects back. And then ray number four is a ray to the vertex that reflects symmetrically around the optic axis. In other words, the angle that is on this side of the optical axis is the same as what you see here. So all of these rays, if you'll notice, when they bounce around, these principal rays, they all cut through this particular point. This is where the image is made. Now, this is for a concave mirror, since this is reflecting over on this side. This is now for a convex mirror. So for a convex mirror, if we look at the principal rays, we're looking at a reflected parallel ray appears to come from the focal point. So in other words, it goes over here, bounces off this way, but if we back project it, it'll cut through right here. Again, we're looking at a ray that goes to the focal point here, and for number one here, we end up doing the same thing. For ray number two, we're looking for a ray toward the focal point and reflects parallel to the axis. So let's follow this one. It comes through and then bounces out this way, and then you can see the back projection not only here, but also here as well. Here you can kind of see where it goes to the focal point and through the virtual image here. And then you can kind of see pretty much the same thing, that the back projection goes to the focal point. The back projection here goes through the virtual image. So for number three, the ray radial to center of curvature, in other words, we're involving the center of curvature, intersects the surface normally and reflects along the path. So in other words, it kind of cuts, it goes boing, boing. But if you back project that, it ends up at the center of curvature. Same type of deal what we had here, where it bounces back, goes to the center of curvature. And then number four, as with the concave mirror, the ray to vertex reflects symmetrically around the optic axis. So in other words, as it comes through here, it makes the same angle as it goes out with the normal here. And then as we back project that, we end up with the virtual image here. So you have, once you found the position of the real or the virtual image point by means of the real or virtual intersection of any two of these four principal rays, we can draw the path of any other ray from the object to that same image point. So here, as far as trying to solve problems for image formation that is done by mirrors, we do the principal ray diagram. The principal ray diagram to geometric optics is what the free body diagram is to mechanics. So when you attack a problem using image formation by a mirror, always draw a principal ray diagram first if you have enough information. Don't draw a lot of other rays at random. Stick with the principal ones. In other words, those are the ones that you know something about. And then if your principal rays don't converge at a real image point, you may have to extend them straight to backwards to locate a virtual image point. We recommend drawing the extensions with broken lines, just like what you saw up here. So you can also color code them if you have the ability to do that. And then you can see if you can identify any known or unknown quantities, make lists of those unknown or unknown, and identify the relationships among them. And then you substitute the known values and solve for the unknowns. So you've got a problem here that you can work through to kind of see what is going on with each one of these constructions. So measurement of figures with the appropriate scaling give you the, okay, so this is all part of that same problem there. That is a good one to work through. I would encourage you to do that. To see what's going on with that, and actually we can kind of talk about it here a little bit. In this example, we're going to find the position of the image formed by a concave mirror using both graphical construction as well as the mirror equation. So a concave mirror has a radius of curvature with absolute value of 20 centimeters. So we're going to graphically construct the image of a real object in the form of an arrow perpendicular to the axis at each of the following object distances. And we're going to check the construction by computing the image distance and the lateral magnification of each image. So here we've got it set at 30. We've got that out here. We've drawn the first ray, which bounces through the focal point, produces the image here. We've got the second one here, which comes here and then ends up, this ray is, I should say, is parallel to the optical axis. The second one bounces through and then becomes parallel to the optical axis. The third cuts through the radius of curvature and of course bounces back. The fourth comes through and makes equal angles of incidence and reflection along the optical axis, and then also cuts through this point right here. If you look at 20 degrees, it's all pretty much the same thing. The only difference here is that if we're looking at our image here and we're trying to draw the one that goes to the radius of curvature, it's going to cut through here. And there's no ray that actually bounces off the mirror to do that. It would go from here to here. So there's no reflection off the mirror. Here, ray 2, if you look at 10 cm from Q to F, ray 2 cannot be drawn because it does not strike the mirror. And then we've got another one here at 5. And so you can kind of see the virtual image that's produced here. So once we take this particular mirror equation and we know what the focal lengths as well as the distance of the real object are, we can go through and we can compute the distance of the virtual image. And again, look at the signs here. They'll kind of tell you if they're on the same side or the opposite side. And also look at the lateral magnification here for each one of these.